start here. Okay. Are you hearing? Okay. Next. Well, I will tell you about the radar technique which you use to detect the subsurface composition, subsurface structures, and to detect, of course, the water, if it's possible, if it exists, of course. Then I will describe a little radar fast and show you the observation with existing radar on Mars, which is Mars and Charat, and I will tell a few words about the water detection, which Enrico just presented, and then tell about the future missions. Firstly, I think that I don't have to convince you that the radar is a very efficient method to probe subsurface. We proved this during the last 15 years with Mars and Charat on Mars missions. And what we detect is that changes in the dielectric properties, structures, and materials. And we use the reflection of waves on these changes on the structures. And this is the way how we proceed. How the radar works. The radar is moving, laser, okay. This is the spacecraft. We have the radar on this. We move in this direction. The pulses are sent with very fast repetition rate. They are reflected by the surface, and we measure the reflected received power of received signal, in fact, and time T1. Then the signal propagates inside. It's reflected by inside. And we see the second peak which arrives. As from the ratio between two, we can detect the properties of the first layer. And of course, we have multiple layers inside, and then we can see all of this. This nice process is slightly perturbed by the scattering and its absorption in the medium, of course. Then what we have, what I say, we have in the best case, you have specular reflection, but you have, of course, the scattering from the surface irregularities. Then this power is not so nice like in specular reflection coming back. Then we propagate the inside, and we can characterize the inside structures. The problem with the nadir-looking radar is following, that the signal coming from the surface on this circle comes at the same time to the receiver. And the signal coming from the subsurface in red here also comes in the same time. It means that you have to have a technique to discriminate between two signals. And this is done firstly by signal processing, which is SAR processing. I will tell a few words after. And the simulations. Simulation is the essential approach in our processing system. Then few words just say. We have the range resolution depends on the length of the pulse, and rather in modern radars on the bandwidth of the signal. And in order to increase our space resolution, we use what we call azimuth resolution. It's along the orbit. We use the fact that there is the coherence between the reflections, between successive measurements, and then we can do what we call synthetic aperture radar. And then we increase the resolutions. For the cross track, it depends essentially on the first Fresnel zone for the sounding radar we have, because our antenna resolution is not very good because we have to use the low frequency, as I will show you here. And then to build the big radar with a good space resolution is very difficult. For instance, for the RIME, we have now 16 meters antenna. On Mars, we we have 40 meters antenna, which is very hard to build in the space. Anyway, what we have here, what I wanted to show here, that attenuation in the materials is depending directly on frequency and on the loss tangent. Loss tangent depends on materials. You can see here, some materials shown here, and for the water ice, the electric properties are constant, it's about 3, and the absorptions, loss tangent, which characterize absorption, as is written here, this is attenuation, it's very low, essentially, for the pure ice, as for the also for the water. And but loss tangent for the brine, it's firstly very big, and the reflections coefficient is also very big. This is used in the new paper from Marcis, I will tell in the end. Anyway, we go here, and for the radar, we have, if you have the basalt, as the previous formula showed, the attenuation is directly proportional to the frequency of the radar, which means that this is scale for 10 megahertz radar, and this is the scale for 100 megahertz radar. You can see that for all materials plot here as function of loss tangent, we can have, for the low frequency radar, we have the losses of the order 30, 40 dB per kilometer, which means that we can use the radar in order to penetrate and detect the signal coming from 2, 3, 4 kilometers. But for the high frequency radar, 100 megahertz, it's not very high, in fact, but we cannot do it because the absorption attenuation is so strong that the radar cannot work. Okay, I think that I have to accelerate. How we measure? We have this just because I will show results, you have to be able to read it. This is the fast time, which means that the time between two impulses of the radar is this scale, and the slow time is the moving of the spacecraft on the orbit. It's in this direction. Let's say each of these measurements is every second. And you will see this cut of plot, radargram, when you have the first reflections in here, it's usually the surface, and the future reflection will happen here. This is our presentation. And here, these are the measurements from Marcis. You can see the long orbit over the South Polar Cap, and this is the reflection from the surface. These are the reflections from the subsurface, but here you have some strange reflections. In fact, we are called this clutter, this comes from the surface. It is why we need to run the simulation of the surface reflection, which we have here, which we call clutter simulations. And you see that these points here, this corresponding to this kind of echo, is just coming from the surface. It's what I showed you before, that there is mixing of the surface and subsurface echo due to the time resolution. This is just topographic map under the orbits. Here I show you the new results which I prepared is the Phobos measurements of Marcis. These are the measurements on Phobos. This is the simulation with the Phobos model, digital terrain model, and of the echo. You can see very good correspondence here between these echoes and this one here, which is just surface echo. All these things are rather the noise, real noise. In simulation, we don't have this kind of noise because it's not, these are the real measurements. And here is the plot of the orbits over the Phobos. Then let's go to Marcis. I'm too long, probably. Okay, Marcis, we have essential differences between Marcis and Charat is the frequency. Marcis is on frequencies from 2 to 5 megahertz, and Charat is 20 megahertz, which means that we have different space resolution, which is 7 meters for Charat, and only 70 meters for Marsis. But Marsis has low frequency. We can penetrate up to 5 kilometers about, and with Sharat only about 1.5 to 2 kilometers, which is difference of what we want to study, of course. Here are the measurements to show you differences of the South Polar Cap. This is the South Polar Cap. On Marsis, you see that we can penetrate up to 3-4 kilometers into depth. On Sharat, there is no way because it's higher frequency, but you have much better resolution. You can see much better layers on Sharat than we see this on Marsis. This we made a few years ago now, the first three-dimensional plot of the South Polar Cap. And you see here the depth, the depth we have here about 3.7 kilometers. And here it's shallower and shallower. And we evaluate quantity of water below the South Pole. And equivalent water level will be about 11 meters over whole planets. In fact, if you add the North Pole, which is plotted here, then we have about double of liquid water on the whole would have if the water is accumulated in polar cap as water ice. And this exists presently on Mars. This is the image of the polar cap, North Polar Cap. And here is the image inverted because the orbits went to the north and other one to the south. And we have here Sharat measurements. You don't see the bottom here. You see very well the structures because we have much better resolution, but you cannot penetrate to the water. Then this year, that's the glaciers, as we are talking about the water, which we observe in the mid-latitude. You see here, this is the surface, and here is in fact the ice water, which means that we have plenty of ice water on North and South Pole, and we have plenty, in fact, the water in the mid-latitude. This is a plot of paper we wrote many years ago now, and this is the dielectric constant of the northern plains on Mars. And you see that this dielectric constant is about less than 3. This indicates, it's the measurements we can have in radar, this indicates that there is plenty water ice inside the surface. It's mixed with, of course, with regolith, etc. But these real dielectric constants indicate that there is water there. Next things. Okay, another things we use I have a few minutes more. Okay, and this shows we made the measurements over the part of North Polar Cap, and we try to determine the properties of the ice inside this part of the Polar Cap. And we found that we have practically pure ice water there, because the electric constant is about 3 to 3.2, with some dust mixed impurities, what we call, which is less than 5, certainly less than 5%, and loss tangent is very low. It's 0.1, 10 to minus 3, and 5, 10 to minus 3. This is obtained from Sharat results, sorry. Then, the last things what I wanted to show is what Enrico told you, the measurements using the Marsis flash memory, in which there is a paper written in Science by Orsay et al., in which they claim that they detect the water. What it here on this plot is the power of the signal coming from the subsurface. This is this blue curve, and red is the surface echo. And this shows that the signal coming from the subsurface is stronger than the signal coming from the surface. this is possible, for instance, because it means that we have really pure ice on the top. And then we have strong reflection coming from subsurface. And this strong reflection is plotted here. You have, this is the region where they measured this strong reflection. And the calculation, let's say simplified calculation, showed that we have very high dielectric constant there. This can be indication of the pure water and the lake, or the brine mixed with water. This is the argument of the authors, but it's still under discussion because others try to find some other arguments to show that it could be other materials. But it's still open, but it's very probable that it's really the water. Okay, and to finish, I think, I wanted to tell you that you have new radars, which is Jewish radar, on Jewish Rime radar, which is a low frequency radar with frequency of 9 megahertz. We had a lot of discussion 10 years ago, 12 years ago, which frequency to choose, because it was not easy, because it was not possible to put, like Mars is the antenna of 40 meters, and we put, of course, it was compromise, discussing using the data we had 10 or 20 to 15 years ago, in fact. And the radar is of 9 megahertz, dipole of 16 meters, it's a big dipole. And we think to penetrate, let's say, up to 10 kilometers, let's say, inside the ice cover of the Ganymede or Europa, we'll see. And the next mission, which will be launched in about 1 year, is the Reason measurement, Reason radar, on which I am also co-I. In fact, it happened that I am co-I on all the radars, planetary radars, sounding radars. And this is very interesting system because we have also 9 megahertz radar, which will give us the possibility to compare results. And you have, in addition, the 60 megahertz radar, which will be used essentially to study the close subsurface and to analyze the surface echo, close subsurface, and to see, because it will work also as interferometer, this 60 megahertz VHF radar. I think that's all what I wanted to say. Thank you.